In this video, I'll go through the effect of changes in bed condition on flow depths. So let's start with the first one. Here we have a lake or reservoir, which means the flow is 0 at the beginning, and at it as the water approaches the slope, then it will gain some velocity. So sorry total head has becomes um, uh, depth d plus velocity. So that's the energy. Total energy h becomes d plus v square over 2g. At this stage, the water is subcritical. Now, depending on the downstream slope, the water depth can be uh, water flow can be subcritical flow or supercritical flow. How we decide if a flow is subcritical or supercritical? We decide this based on the Froude number, right? So if Froude number is V over root GD, right? Now, if so, this equation shows that the critical depth D purely depends on the velocity V, right? So if we are trying to find out what is the critical depth, then we should put F equals to 1, and we can calculate what is the corresponding depth. So we can calculate what is the critical depth. So once you know the critical depth, then and we can compare that critical depth with the actual normal depth of a river flow, this flow. Let's say this is a critical depth, right? If this is a critical depth, then this normal flow is smaller than the critical, so that this becomes this supercritical flow. If the normal flow is here, if the right, if the normal flow is there, then that value is more than the critical flow depth, which means this is the subcritical flow. Okay, and accordingly we define these are the steep slope or mild slope. Okay, so definition of steep slope and mild slope comes from if the flow is supercritical or subcritical. If the flow is supercritical, the slope is steep slope. If the flow is subcritical, the slope is mild slope. Okay, but that comes from the comparison of the water depth with uh, the normal depth with the critical depth. Now, when water moves from the subcritical region to supercritical region, if this is the steep slope and this is the actual flow profile, then what happens at this area, water depth is constant. So at this area from here, it will be D, and downstream from this region, also it has the constant water depth, right? We are talking about the uniform flow. But when it transits from subcritical to supercritical flow, there would be a point where you get this critical depth. Okay, so from this subcritical depth is slowly decreases and it reaches to this critical depth, and eventually uh, and in a smoothly it goes to the critical depth, and then it will be constant, right, depending on that slope. So if the slope is different, this depth will be different, but once it reaches that the normal depth, then it will be flowing in that normal depth. Okay, but between this subcritical and supercritical region, there will be a point where the flow is exactly critical. Now, if the upstream slope is subcritical and downstream slope is also subcritical, if the downstream slope is milder enough to create the subcritical flow, then there will be no critical flow. Now we define the flow depths as the normal depth and critical depth. We can define the slopes also as the supercritical and subcritical slopes. Okay, if this slope that we calculate from the Manning's equation S0 is smaller than the slope that we calculate using the depth for critical flow, then this is called this subcritical. And you can see here, this is the critical depth, right? And the flow depth is flow depth is more than the critical depth. Normal depth is more than the critical depth. That's why it is subcritical flow, and the corresponding slope is also subcritical slope. This region, we can see this is the critical water depth, and the actual normal water depth is less than critical depth. That's why this flow is supercritical flow, and the corresponding slope is called supercritical slope or steep slope. Now what happens if we raise the bed? Okay, if this is a normal bed level, and we want to raise the bed. So initially water depth was d1 and the velocity head was v1 squared by 2g. That's why the energy is d1 plus v1 squared by 2g. Now instead of having this d1, if you raise the bed, then what happens? This depth of flow has to decrease, and to pass the same amount of flow, if the depth of flow is going to be decreased, then velocity has to increase, right? And velocity increase as we increase this bed level. Okay, if we increase it further, then depth will continuously decrease and velocity will continuously increase up to a point where it reaches this critical. Okay, so initially you have this d1 energy point, and you you raise the bed with the height of p, and then what you get? You get this new energy, which is d2. Okay, so this is energy corresponding to d2 and so on. So you can calculate what is the d for corresponding energy. So if you further increase the bed, then what does that mean? The depth has to decrease, so from d1 to d2 to d3 and d4, and eventually it will reach up to dc, or up to critical depth. But if you increase the bed, if you raise the bed more than that, then it cannot go from subcritical to supercritical. So in that situation, what happens is the water depth upstream increases. Okay, so if this is the maximum depth, this is the critical depth, for example, and if you raise the water, if you raise the bed to up to that point, then if you raise more than that, then what happens? The upstream water level will increase. Okay, up to that point, upstream water level will not increase, but if you increase the bed more than that, upstream water level will increase, and that's called the backwater effect. Similarly, if the initial flow was subcritical and you raise the bed, what happens? We can see this effect also from this specific energy diagram. So initially, this was the water depth at which is d1, but you increase the bed, which means the depth of water will be increased and velocity head will be decreased, and you can keep on continuing up to you reach the point which is DC. Up to the critical depth you can increase, so downstream will remain supercritical and upstream will be subcritical. Sorry, the upstream will be supercritical, and at this bed you can get critical depth. But if you increase that, or if you raise the bed furthermore, if you increase the height furthermore, then the water cannot pass. The energy of the water would not be sufficient to go over that raised bed, and in that case situation, what happens is the flow upstream changes from supercritical to subcritical. So the depth of water suddenly becomes from this depth to this depth. Okay, so from it switches from supercritical to subcritical depth, which would be like this. Okay, so significant, then you'll see the significant change in the water height upstream if that happens. Now we talk about this raised bed. What about the lowered bed? It's the same principle. If you lower the bed by delta 0, which means you are adding the energy, and if you are adding the energy, which means if it is the initial was the subcritical flow, then you will get increased water depth. Okay, so initial depth was d1, and now you get the depth as d2. What about this supercritical flow? Initial depth was d1, you lower the bed by delta 0, and if you look at this specific energy diagram, so you go from d1 to d2, which means you increase the energy, but at the same time you decrease the depth, right? You increase the velocity, but you decrease the depth. Now this is an example, raised bed and corresponding flow depth. A rectangular channel is 5 meter wide and 2 meter deep. Okay, so we have this 5 meter wide and 2 meter depth channel. If the discharge in the channel is 5 meter cube per second and the normal flow depth is 1.5, so normal flow depth is 1.5, so we need to use that as in our calculation. So 2 meter deep channel has no meaning in our calculation. We always use the depth of flow. Okay, the channel bed can be like, and the channel section can be very large or small. It doesn't have any impact in the hydraulics. Obviously, if the depth is high, it will be overflow, but other than that, there is no impact. Now, from here, we need to calculate the depth of flow downstream of a section in which the bed rises by 0.2 meter over a distance of 1 meter. Okay, so we need to find out what is the downstream the depth, right? So rectangular channel width, depth, and normal depth of flow y1 and discharge. So from we can calculate what is the energy, right? First, what we need to do is what is the energy at upstream. So energy is v1 plus v1 square by, sorry, y1 plus v1 square by 2g, and velocity is discharge divided by area, right? And velocity head is v1 square by 2g, and if you add that with this depth of water, then we get energy upstream. Now energy upstream it should be same as energy downstream plus the raised bed, right? So we have raised the bed here. That means the energy we can calculate, which is E2 downstream. So this is section 1, section 2 downstream, and section 1 upstream, right? Section 1 and section 2. And at section 2, Y2 equals, sorry, energy equals to Y2 plus V square over 2Z, right? And we equate the energy between upstream and downstream. So energy at section 1 should be energy at section 2 plus whatever is the height of the raised bed. Now energy at section 1 is known, which is 1.522. Energy at section 2 is unknown, but we know this is an equation, y2 plus v2 square over 2z, and we also know this dz value, right? Now we can use this equation to solve for the water depth, right? So energy at 1 is y1 plus p1 square 2, which this parameter is known, which is left hand side. In right hand side we have this E2 plus dz, and in this equation dz is known, which is 0.2 meter, right? So the this dz is known, which is 0.2 meter, and the only unknown is E2, and E2 is y2 plus v2 square by 2z, and in this equation we don't know y, and we also don't know the velocity. So we write velocity in terms of discharge, right? So if you change it like this, so y2 plus velocity is discharge divided by area 2, this square divided by 2z. Now this in this equation the only unknown is y2 and area. Area is d2 times b, which is 5 meter, right? So this in this equation the only unknown is d2, right? We will have all the information and we solve for d2, and you get the d2 is around 1.29, and that will gives this left hand side and right hand side are equal, but you can use any other technique to solve for y2, and that will be the depth of flow downstream of a section.